All right, you guys, today we are taking on chapter 5.7, normal distribution calculations, a little bit more in depth. And I gotta remind you that we need, of course, our lovely Z-score chart in order to work these problems. We will have some shortcuts coming soon, but not until after we assess on next week, Friday. Okay. So here I'm saying find the area, the indicated area under the standard normal curve. It may help to sketch a visual. All answers should be to the nearest 10,000. So I'm asking for 4 decimal spots. So first up here, I see that absolute value notation, right? Absolute value of Z is less than 0.5. So what is that saying conceptually? It's saying that our distance, our magnitude from the mean is less than 0.5 standard deviations. So here, if I make myself a normal curve, right, here's my x-axis, here's my normal curve, my nice bell-shaped symmetric curve. I'm going to put my mean right smack in the middle where the z-score is 0. I'm going to put a little notch here where the z-score would be 0.5. And then over here where the z-score would be negative 0.5. So we're saying again, let me just say that one more time. We're looking for the region where the distance from the mean is less than 0.5 standard deviations. So here's my mean. As I move away from it, where would I be less than 0.5 standard deviations from the mean? And that would be that in-between space right in here. Okay, so that's really telling me then that I'm looking for the space in between the 0.5, the negative 0.5, and the positive 0.5. That's what I'm solving for. So I know that if I look up a z-score of 0.5, it's going to give me an area below, let me pull it out, of 0.6915 right here. And that's telling me my area to the left, my area below that z-score. So I also need to know the area below the negative 0.5. So if I look up a z-score of negative 0.5, that puts me right here, so 0.3085. So again, the z-score, that larger one, tells me the area below. And then here, the z-score of negative 0.5 tells me the area below. So I need to take the small away from the large. So I'm doing 0.6915, take away 0.3085, and that will get me 0.383 as my final answer. Okay, my next one here, we see absolute value again. So absolute value of Z is greater than 0.5. So what is that saying in normal language? It's saying that the magnitude or the distance from the mean is more than 0.5 standard deviations. Okay, so let's make ourselves a visualization of that statement. So here's my normal curve. Here's my mean where the z-score is 0, right? That means I'm 0 standard deviations from the mean. Let me mark those 2 locations, a z-score that is about negative 0.5 and positive 0.5. So we're saying again that the distance from the mean, so distance from the mean, is greater than 0.5 standard deviations. So that's putting us in the 2 tail regions, here and here. And again, we should remember that those 2 tail regions, right, the z-scores have the same magnitude. They're the same distance away from the mean. So we know that the area to the left of the z-score of negative 0.5 will be the same as the area to the right of the z-score of 0.5. And we already solved this in the previous problem, right? If I write this in my basic inequality notation, we're looking for where is z less than negative 0.5 or greater than positive 0.5. That's what we're solving for. So this one, we looked it up in the previous problem right here. So the 0.3085. So that is the area right here to the left of that z-score. So the area to the right of this z-score will match 0.3085. So I end up with 0.617 as my final answer. Okay, I also see that it's really the complement of this answer right here. So the total area under the curve is really 1. So this area right here is what I had solved for here, right? So 1 minus this answer would have actually gotten me this answer too. All right, next a little context. So some word problems. So you take both the SAT and the ACT. You score 650 on the math section of the SAT and 29 on the math section of the ACT. So let me keep those straight. So I'm going to make my ACT, or SAT first. So SAT first, I'm going to underline that 650 for the SAT. And for the ACT, I'm going to underline the 29 for the ACT. So I'm trying to color code. You know I love to color code. So SAT and ACT test scores are normally distributed. For the SAT, the mean is 514. Underline that, right color. And the standard deviation is 118. Okay, for the ACT, the mean is 21. So ACT, mean is 21. Standard deviation is 5.3. So again, we're focusing on the math portion only. On which test did you do better? Explain. Okay, so we're looking at two different distributions. We're looking at the SAT, normally distributed. The mean is 514, and the standard deviation is 118. Okay, if I look at the ACT, it's a normal distribution. The mean is 21. And the standard deviation is 5.3. Okay, so they have totally different scales, they have different means, they have different standard deviations, but they're both normally distributed. So what we're going to do is we're going to find the Z-scores, right? What the Z-scores enable us to do is strip away the units, level the playing field, so that we can compare distributions like the SAT to the ACT on the same scale. So if I find the Z-score for the SAT, Z equals the observation, the 650, minus the mean, the 514, divided by the standard deviation, the 118. Okay, for our chart right now, we're going to the nearest tenth, so we get a Z-score of 1.2. Okay, for the ACT, Z equals the observation, so the score of 29, minus the mean, which is 21, divided by the standard deviation of 5.3. So that gets us a Z-score of 1.5. So let's say that I picture just a little normal curve like this. Here's my mean, Z-score is 0. And I have a Z-score here that's 1.2, and then right here, 1.5. Okay, what I want to be is I want to be the higher Z-score, because I have a bigger proportion that falls below, right? So if I go to the Z-score of 1.2, this would be the proportion that falls below it, the area that falls below it. And here, if I look at that Z-score that's just a smidge above, this would be the area below it, the proportion below it. So the higher the Z-score puts you in a higher percentile, which means that you outperformed a larger portion of your peers. So here we would say the ACT, right, bigger Z-score here means that we outperformed a greater portion of our peer group. So let me just write that in a normal sentence. So you did better on the math portion of the ACT. Okay, we know that a higher Z-score means a higher percentile. Right, so on a test like this, on a standardized test like this, you want to be in the 90th percentile instead of the 85th percentile, for example, right? A higher percentile means that you are outperforming a greater proportion of your peer group. All right, next up, here looking at example 3. So here, same idea, looking at 2 tests, but for grad school. Okay, so the graduate record exam, GRE, and the Miller Analogy Test, MAT, are tests that graduate schools use to evaluate applicants. GRE scores are normally distributed with a mean, so we focus on GRE, with a mean of 1,500, standard deviation of 300. MAT scores are normally distributed with a mean of 50 and a standard deviation of 5. Annie earns a score of 1,900 on the GRE. Bobby earns a score of 43 on the MAT. So let me just underline that. So we're looking at Annie and her score of 1,900 on the GRE. And we got Bobby, who earns a score of 43 on the MAT. So again, if I'm trying to answer a question, who did better, which score is more unusual, right, I need to take it to a Z-score because I need to level the playing field. I need to look at these 2 distributions with the same units. And right now, they got very different units when we're looking at the GRE and the MAT. So we want to strip away those units, level that playing field, and look at it as a Z-score. So which score is more unusual? So that's the question that we're trying to answer. So first, let's just look at what we got. We got the GRE over here. That's Annie. Right, Annie is our key player today, GRE. So here, that distribution is normal. Mean is 1,500 and a standard deviation of 300. Okay, if I find her Z-score, her score was 1,900. Take away the mean for the GRE, 1,500, and divide by the standard deviation of 300. So I get 1.3 as my approximate Z-score. Okay, I want to compare that to Bobby, who is taking the MAT. We got Bobby over here. So for Bobby, his distribution for the MAT, normal, mean is 50, standard deviation is 5. Okay, so his Z-score, here we're saying that Bobby got a 43. So 43, take away 50, divide by 5. So here we get a Z-score of exactly negative 1.4. Okay, so we're saying, well, which score is more unusual this time? So again, if I picture a normal curve like this, here's my mean, my Z-score of 0, and I have the positive 1.3, so Z is 1.3 about, and over here I have a Z-score that's negative 1.4. So which one is more unusual? So we're looking for the Z-score that has a larger magnitude. So if I put absolute value bars around each of those Z-scores, I'm looking for the bigger number overall. So that would be the negative 1.4. So negative 1.4 has a larger magnitude than 1.3. It is a further distance away from the mean. So we're always looking for the Z-score with a greater magnitude, the one that is deeper in the tail region, to tell us which one is more unusual. So Bobby's score is more unusual. Let me start with that. So Bobby's MAT score is more unusual. Okay, again, we know that his MAT score is more standard deviations away from the mean. So again, his has the larger magnitude. It is a larger distance away from the mean. All right, next up. Okay. Adult males have an average height of 5 foot 10 inches. So if I put that totally in inches, we're talking 70, and our standard deviation is 4 inches. Height by gender and age follows a normal distribution. So gigantism, also giantism, is a condition characterized by excessive growth and height. To be classified as a giant, an adult male must be 7 feet, so 84 inches, or taller. So if 5,000 people are selected, how many would be considered giant? Okay, so first let me just summarize the distribution, right? It's normal with a mean of 70 and a standard deviation of 4, all in inches. Okay, so first I need to find out the proportion of individuals that would be considered to be giant. So first I need to go after the z-score. So z equals my observation, so 84. Take away the mean, 70, divide by the standard deviation, 4. So we get 3.5. So a z-score of 3.5 would be that marker for someone being a giant. So a z-score of 3.5 or more. So when I look up a z-score of 3.5, right, there's my 3.5, okay? So this tells me the proportion below. I'm going to need the proportion above. So I need to do 1 minus 0.9998. So 0.0002. Right? So you'd have a really small probability of being a male giant. So now here, that's the proportion of individuals that would be classified as giant. And now we're saying if we take a random sample of 5,000 people, how many would we expect to be considered to be giant? So I'm taking the 0.0002, multiplying by the 5,000, and that's going to get me 1. I would expect to see exactly 1 giant if I randomly selected 5,000 adult males. One of those should be a giant. Okay, next up, what height corresponds to the tallest 5% of males? Okay, so what height? So I know right away I'm solving for the observation. I'm solving for x. I'm solving for the height. And the tallest 5%, right, that cutoff, to use my chart, I have to always think of the lower portion, what falls below. So the tallest 5% would really be the same marker as the shortest 95%. So let me write that here too. So same as the shortest 95%. Okay, the formula that I'm going to use is x equals the mean plus the z-score times the standard deviation. So what I know right now, I know my mean, I know my standard deviation. I don't know my z-score. I have to find my z-score. So to find my z-score, let me just write it first. I need to know, well, what is the area below? What is the proportion below? So I'm thinking shortest 95%. I'm looking at an area below of 0.95. So I need to find the z-score that is closest to an area of 0.95. So if I look at my 0.95, I'm up, oops, let me slide that down. I'm up, more. I'm up in here, right? So I'm looking at where's the area of 0.95 and I see, oh, okay, it's got to be somewhere in here. So is it closer to the 1.6 or closer to the 1.7? So let's check. I'm looking for the smaller difference between the two. So if I take 0.95 and I subtract 0.9452, I get 0.0048. And if I take this guy here, 0.9554, and take away 0.95, I get that that's the difference between the two. So I'm looking for the smaller number. I want the one that it's closer to. I want the smallest value here and here. Let me slide it down. I want the smallest value here and here. Sorry, that was out of your screen. All right, so now you can see it, right? It was closer to the z-score right here. So closer to the 1.6 than it was to the 1.7. Okay, so let me go back to the problem. So I'm saying that the closer z-score is the 1.6. Okay, so now going back to my formula here, my observation, that height will equal my mean. My mean is 70, plus that z-score of 1.6 times my standard deviation of 4. So when I plug that all in, I'm going to get 76.4 inches. Okay, so 76.4 inches, anyone who is above that marker would fall in the tallest 5% of males, and anyone that is below that would be in the shortest 95% of males. All right, what height represents the middle 50% of males? Okay, middle 50% of males. So let's picture this. Let me draw my normal curve. So here's my mean, the z-score of 0, and then I'm looking at about that middle 50%. Okay, so then I know if that's my middle 50%, then out in these two tails, they have to split evenly the remaining 50%. So I got 25% here and 25% here. So if I think of these markers here and here, this area to the left, 25%, and right here, this area to the left, 75%. So I'm looking at my area of 0.75, and I'm looking at my area of 0.25. Okay, so I need to know what are the z-scores that go with those two regions. And I want to remind you that I know that they are going to be opposites because they're going to have the same magnitude. The area to the left, 25%, matches the area to the right, 25%. So if I look up the first one, then I actually know the second one already. So the area of 0.75, boom, right here, that one's pretty clear cut, is 0.7. So my z-score, 0.7. And over here, negative 0.7. Okay, so now I need to figure out what is the height that goes with each of these z-scores. So I know that really I'm going back to that formula that I just used right here. So x equals the mean, 70, okay, plus the z-score, 0.7, times the standard deviation of 4. So if I crunch that, I get 72.8. Okay, over here, my mean is 70, plus my z-score of negative 0.7, times my standard deviation of 4, and I get a height of 67.2. So again, my question is saying, well, what are the heights that represent the middle half of all males? Well, we're saying that it would be anywhere from 67.2 inches through 72.8 inches. That would be the height span for the middle half of our adult males. Okay, I also just want to remind you one more thing. This question is really, really similar to when we ask about the IQR. If I was asking for the interquartile range instead, the IQR, you would have then subtracted these two numbers. So I would have subtracted the 72, take away 67.2, and that would have told me my range of the middle half of data. So I'm just making sure that you understand that there's another way that we ask something very, very similar to this question. All right, one more. All right, a car battery is supposed to last an average of 8 years with a standard deviation of 2 years. If the manufacturer offers a warranty and will replace, this is crucial, will replace 4% of batteries, how long of a guarantee should he offer? Assume that the lives of the batteries follow a normal distribution. Okay, so normal distribution, my mean is 8 years. Standard deviation is 2 years. So if I'm trying to picture what it's saying, what are the 4% that he's willing to replace? Right, here's my mean, the z-score of 0. So he's replacing 4% of batteries. Well, he's not going to replace the ones that outperformed his expectations. He's going to replace the lemons, right? The ones that underperformed expectations. So we're picturing right down here, that lowest 4% right here. Okay, which really tells us that the area from here below is 0.04. So I'm looking for the area of 0.04 and the z-score that approximately goes with it. So if I look at 0.04, let me make sure you can see everything this time. I want to goof up. Okay, so here I'm looking for the 0.04. Which one is it closer to? Is it closer to the negative 1.8 or the negative 1.7? So let's try that again. Make sure that you can see everything on my screen. So if I'm checking, what did I say, 0.04? So if I'm checking the negative 1.8 first. So 0.04 minus 0.0359. That's how far away they are, 0.0041. And then if I check this one, 0.0446, take away 0.04, I get 0.0046. So they're both really close to that area of 0.04, but the one it's closer to is this one right here. So it's closer to the z-score of negative 1.8. Okay, so now I'm going to my observation formula. X equals my mean plus my z-score times the standard deviation. So the mean is 8 years. Z-score here is negative 1.8, and standard deviation is 2. So when I crunch all that, I get 4.4 years. So that would be the cutoff here. So any car battery that lasts 4.4 years or below, right, those are the ones that he's willing to replace because they dramatically underperform expectations. Let me write that as a sentence. So he will replace batteries that last up to 4.4 years. And there we go. All right, I hope today was good practice with normal distributions and the different calculations, especially comparing different distributions, as well as just more practice with solving for the observation itself. All right, I hope you guys are keeping up with the workload, and I hope you have a wonderful rest of your day. Take care.